Energy Canopy. Post-Fossil City Contest 2017. Cars working on fossil fuel. Open plazas with many functions on street level, prone to direct sunlight shining into buildings with no protection from solar radiation. Cities that are densely built up with little space for design improvements to fulfill future energy needs and to solve climate change. These are the challenges presented to us, the same challenges we need to think about when designing a post-fossil city. In the Netherlands, there are currently over 7 million dwellings. Many of these structures were built after the Second World War. Most of the buildings constructed post-war would have low energy labels and have little space for harvesting new renewable energy. How do we fulfill the energy demands for these neighborhoods? By taking advantage of the current situations and improving them. In order to take advantage of the existing structures, it is important to understand the cycle of the sun, precipitation, wind speed, and wind direction. For our design, we work with three objectives. First is to create a sustainable energy-conscious system by using different strategies and technologies that would allow us to harvest energy in the most efficient manner. Second, we want to enhance the urban microclimate, improving the quality of life for people in already developed neighborhoods by directing wind, implementing additional vegetation, and creating shade during the summer months. Lastly, the goal of the design is to provide a comfortable environment in different seasons of the year, improving the quality of the living environment as well as generating ecological awareness for residents in these neighborhoods. Taking these objectives into consideration, we focus first on wind. Currently, wind flows over the relatively flat and rough roofscapes of existing structures. When building heights are terraced, wind speed accelerates. Also, when wind flows around the city blocks, it generates turbulence around the sides. With this in mind, in order to further accelerate wind speed, we create an additional smooth sloping surface on top of the existing roofscape. This allows us to capture additional energy at the end of each block. We use three types of canopy in order to keep winds above a roofscape. First, we establish the height-width ratio between buildings to understand if a wind can continue its path. The second typology is a tree cover, with both existing and new trees planted in larger open spaces to cover the distance between structures in order to keep the wind flowing above a roofscape. The third canopy typology forms a glass layer, mainly placed over existing buildings and sunny open spaces, allowing the wind to continue flowing over the neighborhood. This image is an example of a potential slope canopy in an existing neighborhood. We based our model on 8 design principles for this sloping canopy. First, we created a slope of 16 degrees, which accelerates winds up to 58%, allowing more energy to be captured at lower altitude. Second, by using a smooth surface composed of BIPV solar modules, we provide 13.5% additional energy compared to if the solar panels were placed on the existing roofscape. Third, on hot days, the canopy can open, allowing the wind to circulate, providing a cooling effect. Fourth, the sloping canopy can provide additional shade for sunny days. Fifth, at night, when the long-wave radiation needs to be released from buildings and earth surfaces, the panels open to free the stored heat. Sixth, the canopy can contribute an extra insulation for buildings and energy labels can be enhanced. Seventh, the canopy allows the collection of rainwater, which then can be used for public and private utilities. And lastly, the canopy provides an aesthetic, comfortable environment on the inside that can increase communal use. Furthermore, there are additional strategies being implemented to lower heat problems and give a special character to the neighborhoods. Some of these strategies are shown in this picture, where a wind energy generating structure is presented at an entrance. This feature symbolizes and emphasizes the focus of a neighborhood on renewable energy. Also, there will be some intervention on street level to improve the microclimate by evapotranspiration and shade. Since vehicles would need a charging station, some small streets can be released from traffic in order to create more permeable streets and improve the local microclimate with vegetation, lowering AC consumption of the households. Finally, permeable surfaces for parking with available charging stations would be located in convenient locations. Thank you. We hope you enjoyed our presentation.